Today we're going to look at a Taylor series. This is section 9.2 in your book. Taylor series, Brooke Taylor, an accomplished musician and painter, did a lot of work concerning Taylor series, and this is why it's named after him. Our objective today is to find a MacLaurin approximation and a Taylor approximation of two elementary functions. Now I'm sure you're asking yourself, what exactly is this? Well, a Taylor polynomial and a MacLaurin polynomial allow us to approximate functions using polynomials. We can approximate what sine x looks like by using a polynomial. We can approximate what the natural log of x looks like by using a polynomial. On page 1 of your notes, you see the formula for MacLaurin series. This is just something that you have to memorize, you have to know. And also for a Taylor series. The only difference between a MacLaurin series and a Taylor series is that a Taylor series is centered at something other than 0. In this MacLaurin series, notice that it's centered at x equals 0, and that doesn't make any sense to you now, but it will as we continue to do this. So the way we do it is we evaluate the original function at 0, then we take its first derivative and evaluate it at 0, then we take the second derivative, evaluate it at 0, and now we're dividing by 2 factorial. And then we take the third derivative, evaluate it at 0, and we divide by 3 factorial. Notice that we're going from x to x squared to x cubed. So the third derivative is the coefficient of x cubed. The third derivative divided by 3 factorial is the coefficient of x cubed. A Taylor series is very similar. The only thing is that it's not centered at 0. So now instead of evaluating the function and its derivatives at 0, we evaluate it at a, where a is the center. And so if you notice, these formulas are very similar, but instead of just having x multiplying by x, we now multiply by x minus a. Please take a moment to become familiar with these formulas. You have to know them. So let's do an example. In this unit, we're going to do this unit a little differently than previous. We will do a few examples on the video, and we will do a few examples in class. That's just because this unit is so much fun. I don't want to deprive myself of seeing your glowing faces as you discover this new information. So we're going to approximate the natural log of x plus 1 using a MacLaurin polynomial, and it's a MacLaurin polynomial simply because it's centered at 0. So our first step is to evaluate the natural log of x plus 1 at 0. Now we're going to take the derivative of the natural log of x plus 1. Using chain rule, we get 1 over x plus 1. We're going to evaluate this at 0. We're going to take the second derivative and evaluate it at 0. The third derivative, evaluate it at 0. And the fourth derivative. Now the reason I did up to the fourth derivative is because if you look in your notes, it says find a MacLaurin polynomial with 4 terms. That really should read to the 4th degree. So we're finding a MacLaurin polynomial of the 4th degree. And if I'm going to the 4th degree, that means that I need 4 derivatives. So we're going to take the values that we just obtained and evaluate the formula that I gave you using those values. So I'm simply just exchanging the values here. F of 0 becomes 0. F prime of 0 becomes 1, so we'll have 1x. And I'm just exchanging the values that we calculated for the and placing them into the formula. So this becomes a polynomial that can approximate the natural log of x plus 1. If I were to graph the two functions side by side, notice that f of x is the actual function, the natural log of x plus 1, whereas p of x is the polynomial in red. Notice that between -1 and 1, the values are very similar. But after about a little bit before 1, the values start to depart. And the further we go away from the center, the further the values depart, the more error is in the polynomial. But we can see from about -0.5 to 0.5, the values are very similar. I want you to think about what we could do to make it more accurate. Let's think about some of the things that we could do to make it more accurate, and we will talk about that tomorrow. Okay, so now we're going to do, if you go to page 2, because like I said, we're not doing all of your notes today. So if you go to page 2 in your notes, this is our second problem. This time we're finding a Taylor polynomial. The reason it's a Taylor polynomial because it is centered at 2 and not at 0. But we're going to do the exact same thing. We're going to start by evaluating f of 2. Then we're going to take the derivative of f of 2. And that actually should be, f of 2 should be 1/4. No, it should be 1/2 because it's 2 on the top. I'm sorry. So the derivative of f of x is -4x cubed, and we evaluate that at 2 as well. Then we take the second derivative, evaluate it at 2. We take the third derivative, evaluate it at 2. And then we take the fourth derivative and evaluate that at 2 as well. Now we're going to take these values and substitute them into the formula that we were given. We can clean this up by multiplying this out. So what I've done is 3/4 divided by 2 factorial ends up being 3/8. 3/2 divided by 3 factorial ends up being 1/4. And so on and so forth. So I've approximated this function with the center at 2. Also notice that my variables now are x minus 2, x minus 2 squared, x minus 2 cubed, x minus 2 to the 4th. That's one of the biggest mistakes of calculus students, is forgetting when we do a Taylor polynomial, it has to be x minus the center. Okay, so that's pretty much it for today. So the thing you need to remember for today is that a Taylor and a MacLaurin polynomials are used to estimate functions. A MacLaurin polynomial is a Taylor polynomial centered at 0. That's the only difference between the two. There is no homework tonight, and we will finish working on examples tomorrow in class, as well as hopefully begin homework. Have a good afternoon.